Operating a massive global video sharing platform requires a physical footprint of thousands of highly interconnected data centers. Users upload 500 hours of video every minute, generating 720 terabytes of raw storage daily. Yet this intake is tiny compared to the read volume. With 5 billion daily views, egress hits 5.8 terabytes per second, one upload for every 1,000 views. Uploads and processing can safely take several minutes without impacting the creator's experience. Playback demands the opposite. Streaming requires a time to first byte of under 200 milliseconds. Time to first byte measures the duration from the user's initial request to the arrival of the first piece of data on their device. Standard monolithic web architectures fail under this asymmetric load. If long-running upload connections and instant video playback share the same server resources, the heavy uploads will saturate the connection pools and cause the streams to buffer. Sustaining 5.8 terabytes of throughput requires two isolated pipelines, an asynchronous ingestion factory, and a globally distributed delivery network. In a naive ingestion model, a client attempts to push a 1 gigabyte raw video directly to the API web server. Transferring this takes minutes, occupying a connection slot. At scale, thousands of concurrent uploads exhaust these slots. This exhaustion crashes the web tier, taking the platform offline. A smart bypass prevents this by having the user send only a lightweight upload request to the API. The API functions as a traffic controller, verifying authentication. Once authorized, it provides a presigned URL, a temporary key granting direct write access. The client uses this to push the 1 gigabyte payload directly into S3, bypassing the API entirely. This decoupling allows the web servers to process millions of lightweight requests, while the heavy data ingestion is handled by scalable object storage. When the S3 bucket finishes receiving the raw file, it fires an event notification. This flows into Apache Kafka, a distributed event streaming platform that queues asynchronous messages for downstream systems. This queue functions as a shock absorber. If 10,000 videos upload simultaneously, the queue safely holds the jobs, preventing servers from being overwhelmed. A cluster of transcoding workers, servers optimized with high-performance GPUs, pulls the next available job from the queue. They convert raw camera files into standardized web formats. High-resolution 4K files are computationally expensive. Transcoding a feature-length video linearly on a single worker takes hours. To eliminate this bottleneck, the system employs a split and merge strategy. The raw video is sliced into segments and distributed across 50 worker nodes for parallel processing. The workers generate multiple quality buckets, from 360p to 4K. They fragment these resolutions into 5-second streaming chunks and create a manifest file to index their locations. This event-driven architecture transforms what would be an unpredictable, chaotic write load into a smoothly paced, highly parallelized digital assembly line. Delivering high-definition video over mobile connections causes constant buffering as signal strength fluctuates. Maintaining low latency requires shifting routing intelligence away from the central server and onto the client device. This is the setup for adaptive bitrate streaming. Adaptive bitrate streaming is a technique that adjusts video quality based on real-time network conditions. When a user clicks play, the device first downloads a lightweight manifest file that lists all available resolution tiers. The video player calculates the device's current internet speed and determines which quality tier it can download without triggering a buffer. If a user watching in 1080p on home Wi-Fi walks out of range, their connection drops sharply. The client detects this, references the manifest, and requests the next chunk from the 360p bucket instead. The video quality pixelates, but playback and audio continue without interruption. Even with adaptive streaming, physical distance creates latency. Pulling a data chunk from a United States database to a phone in London exceeds the 200 millisecond time to first byte limit. The system uses a content delivery network, a global group of edge servers that store copies of video chunks directly inside local internet service providers. This model achieves global scale by using client-side logic to request fragmented data from the absolute closest physical edge node. The underlying data layer must seamlessly handle billions of daily metadata operations, storing titles, descriptions, and rapidly updating view counts. Storing all of this information in a monolithic SQL database creates a critical failure point. When a viral video is uploaded, millions of concurrent users attempt to increment the view count simultaneously. To prevent corruption, SQL databases lock the specific row. Millions of requests queue up waiting, causing the database to crash. Heterogeneous storage addresses this by separating data based on access patterns. Core metadata, requiring strong consistency, stays in a sharded SQL database, distributed across multiple machines using a hash of the video ID. High concurrency metrics like view counts move to a NoSQL database. NoSQL systems are non-relational databases designed for massive parallel operations. They allow millions of updates with eventual consistency without row locking. This architecture maps specific data stores directly to the read and write behaviors they are intended to serve. Supporting 1 billion daily active users requires defensive engineering. At this scale, hardware failure and data corruption are constant occurrences. If a corrupted file repeatedly crashes a transcoding worker, the job is moved to a dead letter queue. This is a specialized storage area for failed jobs that allows the main pipeline to continue while the corrupted file is isolated for manual inspection. The system also faces the thundering herd problem. This occurs when 1 million users request a new viral video that hasn't been cached in the local CDN yet. The CDN uses request coalescing to collapse these million requests into a single fetch from the origin server, preventing the central database from being overwhelmed by a sudden spike in traffic. These engineering protocols maintain absolute uptime by isolating individual failures and throttling internal traffic spikes. This unified architecture shows how specialized components function as a single global machine. The write pipeline uses presigned URLs to bypass web servers and asynchronous queues to manage ingestion rates. The read pipeline utilizes adaptive bitrate streaming and edge caching to ensure low-latency playback across any device or location. The data layer shards consistent relational data while delegating high-velocity counters to NoSQL stores. Sustaining 5.8 terabytes per second requires decoupling every component, shifting processing to parallel workers, routing logic to the client, and data to the network edge.